Thank you for the good introduction. So yeah, I'll be talking about, I will start with an example of something we did recently with my students, Perry and Alexander, and then spend some time reflecting a bit about what we did and what opportunities and challenges we can find in this activity of formally represent architectures and what is this and how that works. Right, so this is an example we work on, an on-chip network, a ring network called Tornado. And the basic idea is to have rings in horizontal and vertical directions. So here you have rings going east to west and back, and north, south, and back. So you have in this 4 rings that way and 4 rings in the other directions. And it's a system, and we're interested in system level modeling, so they have blocks, and every router is composed of different blocks, and basically 4 times the same basic block called a ring stop, and then some memory to store some messages. And what's happening in this network is that you can travel from one ring to the other, and then reach your destination. And of course, they have some restrictions in a number of changes you can make to avoid deadlocks, where you can go from one ring in the horizontal way, then go vertical and back horizontal and create deadlocks that way. And the basic idea of this ring stop is to get a message as the input and then decide whether this message has to be routed to another ring or ejected of the network, or should be forward propagated on the ring. And then they have injections where you can inject new packets on the ring. This specific ring networks has some special features. One is they call spillover, where the idea is instead of blocking traffic, if you're waiting to be ejected here in this intermediate buffer, you are spilled to the ring, and that you keep traveling further on the ring and you will come back, and they have a kind of sequence numbering mechanisms to make sure that you will not be spilled infinitely often. At some point, you will have the highest priority, and you will get the turn to acquire this resource, this queue. And they have constraints in injections, because in these rings, if you fill the rings with packets, at some point you get blocked because the ring is full. And what they have is they have the constraint to say you're only allowed to inject a new packet in the ring if this ring buffer is empty at the ring stop. So they have a constraint that you limit the number of packets to make sure that you still have one free slot in the ring to move packets around. And they have a complex, fancy inflation mechanism where even if everything is stuck, completely full, then they have a way to extend the network by 1 to create an extra slot and resolve this contention. And the exercise we had was take this paper, read it, and try to make a formal model of these systems and try to prove liveness. So we're interested in proving that packets never get stuck on their way, that every time a packet reaches a queue, then it can always move forward, either to the next queue or to be ejected of the network. And what we use is MADL, Macro Architectural Description Language, and it originates from Intel's Xmas. So we work together with Intel in defining this executable macro architectural specifications. And the basic idea is to get a small set of primitives of these blocks here on the screen, queue functions, sort things, where for each one of them you have a very precisely mathematical definitions of their behavior, and you compose them, and then you have a graphical model that is your formal model. And then every primitive, they communicate using a kind of handshake protocol where you have an iReady to say, I have data to transfer. Then the other primitive has a TReady signal that is raised where the other primitive is ready to accept the data. And when both signals are high, then the data is flowing from one primitive to the other. And in that case, we can express this deadlock liveness property as there is a point in time in the future where this iReady signal is high, and from that time, from that point in time, then always, globally, the TRD will be low. So we reach a state where there is a queue or primitive which has some data to transfer to the next one, but the next one will never be able to accept the data. Right? And it's a known property to be hard to check, and we want to do it with systems with tens of hundreds of primitives. Right? So we build our own extension of these graphical notations where we have our own language with type declarations, type checking, parsing, and everything. You can find it on GitHub. And we're defining a small graphical interface where you can draw these signals, draw these blocks, create your macros, have some properties, have some kind of waveforms where you can look at the counterexamples to make it easier to be used. So the first thing we had to do is to extend the language because we couldn't express the fact that you have to give the turn to these inputs only when this queue is empty. And in the theory, to make this efficient, this is just not possible. So we created a new primitive expressing this constraint to say, hey, here you have a kind of arbiter. You have to choose between this queue and this new packet, but you can only give the turn to this guarded input when the queue is empty. And this allows us to model these rings and to automatically detect them. So once you insert those queues, those guard queues, and somehow we can follow them and discover rings. So here, for instance, you have a blue ring where you inject blue packet here, then they will go either to their destination in this first ejection queue or be spilled back and for another lap. And the same happens for the red packets that also go one round or are ejected. And the idea is to find out for all the possible colors, all the possible packets, to discover all the possible rings, and then try to combine them together to reach a point where we can define invariants about these rings. And the invariants say that the occupation of the ring, so the maximum number of packets that can be stored in the ring, is at most equal to the capacity of the ring, so the maximum number of slots that we have in the ring, the maximum number of places in the queues, minus this smallest guard queue we have. So somehow we know from this guard queue that we have this constraint that you're only allowed to eject new packets if this is empty, and the information we want to gather from this primitive that the consequence is in all these queues you have at most the number of packets, here you have 2, 4, 6 places, minus, let's say, these 2 places here that must be free at some point. So you know that you have 2 places free all the time. And this allows us to quickly discover that these deadlocks where you have all the queues that are full, it's just impossible to reach. And we can quickly decide that the liveness property holds for this ring. So once we have this guard queue, we can start modeling the architecture, try to find a way to express some of the features of this network. So here we have our model of this ring stop, where we have here a decision point where you say, is the packet to its destination? Has it arrived to the destinations, or should it be ejected to another ring? Or should it be forwarded further down the same ring? And here we have a bit somewhere that say, have you been spilled or not? And we model the fact that you cannot be spilled infinitely often. So at some point, you need to have this bit set to high, and you have to wait for this resource here. And here we have a non-deterministic choice where we can abstract away from the decision to spill or not. And then you either go for one lap, and then you spilled, or you not spilled for some reason, and then you have to be ejected. And we use this non-determinism to abstract away from details and make the analysis more scalable at the end. And of course, at the price of some features that are not precisely modeled in this experiment. Once we have the block, we can put them together. So we have all these blocks here with some memory in the middle to store all these packets. And then we can start to create larger networks and see how well do we scale. And we managed to get to 8 by 8, and that's getting close to the maximum we can do. And 64 nodes, every node has 4 of these small blocks. And we see that the time is dominated by this computation of this ring invariance. So we have to find all these rings, and we have to combine them all together. And the number of rings grows exponentially with the size of the network, and we have to combine them all together all the time. So we have to do many of these comparisons to find out the right rings. But still, it's a system, and we can prove liveness for these large systems. So what we did is, at the end, so we managed to formally model this network and find some deadlocks that were not foreseen in the paper. And of course, we want to do more, model these inflation mechanisms and everything. And I'd like to spend the last 5 minutes to reflect a bit about what we did. So what we did is a kind of early modeling prototyping thing where you took the paper, and we did this for some more concrete, some other examples with partners, where you take the paper and you try to build a formal model of it. And it can be seen as formal modeling. It's being done in the industry. I'm talking here to some engineers. They really do it. It's great. But it's done in an ad hoc way. And I think one of the opportunities I see is, can we do research to support this, to find the tool, the methodologies that will help that? Because right now, engineers are doing whatever they can, whatever they have, and every engineer does it a bit in its own way. So there are a lot to do. What we see in the industry, also in academia, is how to automatically abstract from the implementation back to this abstraction, these architectural models. This is done manually in practice, where you hire some expert that can look at your design and create those abstract state machines, connect them, do some tricky formal analysis, and tell you whether there is a deadlock or not. We try to automatically recover these Xmas models from RTL, but this is very difficult. We had some results, but not the ones we wanted. Finally, what you can do with these models is refinements. Take one model and then solve this non-determinism points where you say, no, I want to have the decision. I want to model this particular decision is no longer non-deterministic. I want to make a model of it and refine your models. And what are the refinement relations we need to maintain these liveness properties? This is also an open question. And finally, what we see in the software industry is a lot about model-driven engineering, where you can do many things with your model. And for now, we haven't explored those directions very much, where you could have this model and why not generate the RTL from it? Or even your documentation, your papers. You have this executable mathematical representation of your system. You can transform it in different ways. And yeah, I think the opportunities are to try this out, see how far we can go. And the challenges are, of course, scaling. We need to be able to represent quite complex systems. If you only have a few blocks, then this is not really interesting. The game becomes interesting where you have tens and maybe 100 of these blocks. And in this generation here, we have to fight against very smart engineers to be able to generate code that is acceptable, which is a challenge. So yeah, I think that's what I wanted to say. Many opportunities, I think a lot of work to be done, and thank you for your attention.
Well, thank you, and do we have some questions?
I'm curious to know why you chose that particular formal modeling language, and I'd be interested in your thoughts on your preferred other formal modeling languages.
Yeah, so the question is why to use this model? So we invented it, so we like it, because it's our small baby. But The reason is that it scales in the analysis. So there are some restrictions in the semantics of the language that allows us to have this invariance, this information about the structure of the entire system. And from that, we can boost all these formal engines, and we can scale to tens of state machines, for instance, where if you do it in a naive way, in system Verilog, for instance, you will not be able to prove the liveness properties that fast. So we technically we translate this property to a safety one, and then we can scale. And to make these translations, we need the restrictions that are in the language. So you could use another language, but I guess you will not be able to scale as well as what we do. But I'm happy to take.
I'm curious to know, for instance, are you aware of Adam Chipala's work or Peter Stoll's work in formal modeling? And how does this compare against Sale or against Adam's formal modeling work?
I've heard of it, but I do not know the details. If you can point me to some papers, I'd be happy to look at it. But I don't know the details to compare.
Okay, I'll come and talk to you after.
Yeah, sure. That'd be great.
Hi, I was just interested in how easy it is to change the topology of that network and to exploit your model with a different topology.
Oh, yeah, so the question is how we restrict it to rings? Or,
Yes.
Yeah, so in this work we targeted rings because we couldn't do them before. So we had done meshes and some other kind of trees and any topology you want. It can be also completely irregular. We don't have any restrictions over there. So if you have any custom hierarchical topology, then it's okay. There is no restriction about it. It's just for the rings, we had no ways to detect, to restrict the fact that you cannot inject so many messages in every rings. The contribution was to say, let's have this God Q primitive so that we can extract these invariants and be able to analyze them. So we targeted rings because we couldn't do them, but we can do the other ones.
So you talked about being able to detect deadlock and prove that that's not occurring. Were you able to prove that things would terminate? You did allude to that, but were you able to prove termination properties and make sure things wouldn't just sit in running around the rings forever?
So it's a good point. So in those rings especially, then you can spear forever and never somehow change anything. So you have potential live logs. And we had this detection in it, so we try to find out cycles where you do not change your packet, and that's a possible live log. If it doesn't change and you come back to the same state, then you can somehow have a potential deadlock. We don't have a live log, sorry. We don't have other ways to prove it. It's a tough thing. So we somehow make assumptions to prove the deadlock freedom, and then we need some kind of other analysis to do the live log ones. And we're now looking at how can we combine them together. And if you want, we assume no live logs, and we can prove no deadlocks. And if you assume no deadlocks, you have no live log. But sometimes they influence each other, and we have to find out how to do that. So we need some more study and more theory to analyze and study this interaction between these live logs and deadlocks.
So are your results parameterized on the sizes of the buffers, or does it hold for any particular size?
Well, the question is how we're depending on the size of the buffers. Yes and no. I think that in practice, we could probably formulate it by keeping them as symbols, and we use SMT under the hood where they can deal with this. But sometimes when these methods fail, we fall back to reachability, where we have to take into account the size of the buffers. So they play a role, but not always.
Let's thank our speaker.
Thank you very much.